Hello, everyone. My name is Andrew Kim, and today let me start a review session for AP Physics C RLC Circuit. Now, I remember doing the same review session last year, simply because this unit is the hardest unit in AP Physics C. Some people might think that flux and electromagnetic unit might be also hard. Well, that is true, but RLC circuit can also be very complicated in both school tests and even an AP exam. So I will go through this unit, and I hope this helps you a lot. Also, I'm going to go through the basics of circuits. So if you have hardships in those units as well, then this review session will be a great help to you. So let's get started. Okay, so what we're gonna do first is we're gonna start with the basics of circuits. And I believe the most basic formula in circuit is V equals to IR, which is also called Ohm's law. So now what's special about this law is that once you know two of the three variables, so two of either V, I, or R, then you can find the other one by using this formula, V equals to IR. And resistor, voltage, and current appears in pretty much every single circuit, so this can be a lot of help. Now, what's interesting is you can also calculate P using V, I, and R. And the formula is P equals to VI. And if you look at this formula, V equals to IR, you can change this VI into either V squared over R or I squared times R. So even though you don't know V or even though you don't know I, still you can use alternative formula like V squared over R or I squared R in order to calculate P. Now, P is a characteristic of the resistor. And this is obvious because you can see in the formula, as you can see in the formula, there's R involved. So R, or the resistance of the resistor, affects P, which means P would be the characteristic of each resistor. That means that if you have multiple resistors, then each resistor might have different R. So you would have to calculate the R, might have different P. So you might have to calculate multiple P's for different resistors. That being said, let's go over to the next part of the circuit, which is capacitors. Now for capacitors, the most important formula will be Q equals to CV. Q is basically the charge that is charged in the capacitor. C is a physical trait of the capacitor. And now this word physical trait is very important because depending on V, depending on I, depending on whatever characteristic of the circuit, C does not change. The only thing that can change C is the capacitor itself, how the capacitor looks like. What's the distance between the two plates of the capacitor? What is the area of the capacitor? Those are the only characteristics that can change C, because C is not something that's affected by the circuit, but it's a physical trait of the circuit itself. So you would have to know that. And finally, V is, as you know, voltage. What voltage is it? It's the voltage across the capacitor. So now you have the formula Q equals to CV. And also, you can calculate the energy stored in the capacitor by using the formula U equals to 1/2 times CV squared. Now, similar to above, similar to P here, you can use this formula Q equals to CV to change this formula, U equals to 1/2 times CV squared into either Q squared over 2C or QC over 2. Now, some people might find this formula hard to memorize, but in fact, it's not, because we already know the formula K, EK, or the energy, the kinetic energy, equals to 1/2 mv squared. Now, if you compare this and this formula, you can see that they are literally identical. The only difference is that M in the kinetic energy formula is changed to C for the energy stored in capacitor. And V, well, interestingly enough, they're written in the same alphabet, although they mean different things. The V over here for kinetic energy would mean the velocity of the object, while V over here in the capacitor would mean the voltage across the capacitor. Now, another thing that's important to remember in capacitor is that when capacitors are connected in parallel, then they have the same V. And when the capacitors are connected in series, then they have same Q. Why? Well, it's very obvious if you think about it. If the two capacitors are connected in parallel, then the voltage across the two capacitors would have to be the same because this red part of the circuit and this blue part of the circuit are both disconnected by two capacitors, C1 and C2, which means the amount of voltage that drops through C1 and the amount of voltage that drops through C2 should be the difference in voltage in the red part of the circuit and blue part of the circuit. In other words, the amount of voltage that drops through C1 and the amount of voltage that drops through C2 should be the same. Thus, the voltage is the same and same V across the capacitors when they're connected in parallel. Now, if you think about Q, what's interesting is that let's say we have positive charge charged in the left plate of the left capacitor. Let's say this amount is plus Q. Then what would be the charge in the left plate of the right plate of the left capacitor? Well, that would be the opposite charge of the left plate of the left capacitor, thus negative Q. Now, what's interesting is if you think about this green part of the circuit, then since left part of the green circuit is charged with negative Q, the other side or the right part of the green part of the circuit would be plus Q. Thus, the left plate of the right capacitor would be charged as plus Q. And since the left plate of the right capacitor is charged with plus Q, the other side of the same capacitor or the right plate of the right capacitor would be charged with negative Q. Thus, same amount of Q or same amount of charge should be charged in both capacitors when they are connected in a series. So that's one thing you would have to know. Now, we are going to start talking about something more complicated, something this unit actually deals with, which are joint rule and Kirchhoff's rule. However, before going through these two, I would like to introduce an interesting analogy, which is water flow analogy. Now, water flow analogy is basically thinking of water flow or water pathway instead of circuits because it's simpler. Now, we can think of a water pathway with pumps. Let's say this thing is a pump. I'll write P over here. Pumps the water up, and there's a downhill that makes the water flow downward. So we have a water flow something like this. It's a very simple water pathway, but it's good enough to explain how the circuits work. So in this water pathway, each water particle would mean electrons in circuits, electric circuits. And water flow in this water pathway would mean currents in electric circuits. Water pathway itself, the root in this water pathway would mean circuit itself in electric circuit. The battery in electric circuits would mean pump in this water pathway. The downhill over here in the water pathway would mean resistors in electric circuits. Finally, the height difference or the height in each point of this water pathway would mean voltage in each point of electric circuits. Now, I'll explain how this analogy actually works. Now, if we think of this water pathway, we have water particles moving in this water pathway, and the pump pumps the water particles up using energy, and this downhill actually allows the water particles to use up their energy, use up their potential energy in order to flow down. Now, this is exactly the same as how circuits work, except just one thing, which is that in electric circuits, the electrons move the opposite direction of circuit. But that's not a big difference because, in fact, electric circuit was designed under the assumption that electrons move in the way of the electric current. Scientists thought the way the current moves is also the same as the direction of the electrons moving. However, later it was discovered that that's not the case. In fact, electrons move the opposite way of the electric currents. However, that didn't make a huge difference. The only thing that was changed is the knowledge, the information that the electrons flow in a different way than the current, and how the current circuit works, how we calculate voltage and everything did not change. So this one small difference will make a big difference in understanding this concept. So let's get over with it. So if we think about water flow, if we think about current, we have the current moving just like how the water flows through the water pathway. We have the water pathway, the root, just like how circuits move in the currents move on the circuit. Now we have battery, which pumps up the water flow or the water particles using energy, just like how batteries use up energy to pump up electrons to move in a certain way to create current. We also have resistors, which literally uses up the electron's energy or the current and reduces the current. It doesn't reduce the current, but it reduces the voltage, which is the electric potential or the height. So you can see how battery increases the height of the water using energy, which is equal to increasing the voltage or electric potential of electrons or current using energy, whereas resistors pulling down the water, decreasing the height, which is equal to the resistors in the electric circuit pulling the electrons down and decreasing their voltage or electric potential. So this analogy helps understanding most of the circuit concepts. For example, if we go up here, let's look at this situation where we have capacitors and why the voltage across the two capacitors connected in parallel should be the same. Basically, it's like two downhills. We have two downhill, C1, and another downhill, C2. What's interesting is the height before C1 and C2 are the same. It's the red part. And the height after C1 and C2 are both the same. It's the blue part. Thus, since the height before and after C1 and C2 are the same, of course, the height difference of slide C1 and slide C2 should be the same. Thus, V across the two capacitors are the same. Now, some people might say, wait, Andrew, didn't you say that downhill is equal to resistor, not capacitor? Well, you are true, but we know that capacitors also work as decreasing the voltage or decreasing the height in water pathway. Thus, it works the same as resistors. Capacitors work the same as capacitors in terms of voltage and current flowing. Although the current flowing works in slightly different way than resistors, because in capacitors, the I or current is not stable. It changes over time. But still, how the voltage decrease when it crosses capacitor is exactly the same as how the voltage decreases when it crosses the resistors. So if you're confused, if you're wondering where would the current flow or what would be the voltage difference in those things, then it's good to think about this height. Which place is higher in the water pathway? Once you think about that, then you will be able to know, oh, this part of the circuit is higher than the other part of the circuit, so the current would flow from the higher height point to the lower point. So this is one analogy that's good to use. You can use this literally in every single concept in circuits. And now I'll move on to the main part, which is joint rule. So joint rule is basically input equals to output. So if you have this joint, a junction, where three branches of circuits meet, of course, there would be input, there would be some electrons moving towards the junction, then the current moving out of the junction should be equal to the current moving in towards the junction. So I1 equals to I2 plus I3. Of course, this equation might change if the junction looks different, if the junction looks like this, if currents are moving from two parts of the branch and it's moving out of only one part of the junction, then I1 plus I2 would be equal to I3, not I1 equals to I2 plus I3. The whole point of this is that the amount of current that's flowing in towards the junction is equal to the amount of current that's flowing out of the junction, which, again, if you think about this water path analogy, is obvious. Of course, the amount of water that flows into the junction should be equal to amount of water that's flowing out of the junction. So same, even in electric circuits, the amount of currents that's flowing towards the junction should be equal to the amount of currents flowing out of the junction. Now let's move on to Kirchhoff's rule. Now what Kirchhoff's rule is saying is very obvious again. Basically, if you define a closed circuit, if you define some type of closed circuit like this, I don't know how it would look like, but whatever. Let's say there's a closed circuit like this, then delta V equals to 0, which means if you travel through this circuit, then the voltage difference, the change in voltage should be 0. So if you think about, let's think about something simpler, because obviously the one I just drew has a lot of components and it's going to be hard to explain. So let's think about this. Let's say you start from this blue point and move in a clockwise direction. Well, the first voltage difference that you will experience is this V1, and that will be an increase in the voltage because you're moving toward the direction of the battery. So your voltage difference would be V1. Now, if you move towards R1, or the first resistor, your voltage will decrease because you're moving on the direction of the resistor. So you would have some amount of voltage decrease. Let's say that's V2. Again, you meet the next resistor, and same thing would happen. Your voltage would decrease because it's a resistor. So you would have V3. And what Kirchhoff's rule is saying is that this should equal to 0. Well, it's not a very complicated theory itself, but if you use water path analogy, again, it's going to be way easier to understand because, again, what was V, or battery, in water path analogy? It was the pump. What was R1, or resistor, in water path analogy? It was a downhill. Now, what was R2, or the second resistor, in water path analogy? Well, it was the downhill again. So what this Kirchhoff rule is saying is that basically, if you have a closed circuit, if you have a closed water pathway, then if you move up through a pump, and if you move down through a downhill, and if you move down again through a downhill, then your height would be the same as the initial height, which is very obvious. I mean, if you go through one circuit, one water pathway, and if you come back to your initial position in the water pathway, of course, your height should not be different because you started from the same point and ended at the same point. So in that point, the height should remain the same. Thus, the height, again, in electric circuit is the voltage. So what Kirchhoff's rule is telling you is that not the height is the same, but the voltage would be the same. Thus, there is no change in the voltage if you go through a complete closed electric circuit. So again, water path analogy helps you a lot. So yeah, that's the whole point of Kirchhoff's rule. And this gets really handy when you want to find, for example, resistance or the amount of current that's flowing in certain part of the circuit and stuff like that. And one thing you would have to keep in mind is that you don't always know where the current would flow. For example, in this image, in this drawing, in this circuit, you know, obviously, that the current would flow in the clockwise direction because you have the voltage like this. However, in some complicated circuits, it's hard to assume the direction of the circuit. In those situations, just make an assumption. You might be wrong, you might be correct, but that doesn't matter. Just make an assumption, and I'll show you how that works. For example, let's say you have a circuit, something like this. And this showed up in one of my unit tests. Now, it's hard to assume the current in the middle part of the circuit because basically what this red battery induces is this battery induces circuit this way, and this green battery induces circuit this way. The two battery induces currents in opposite directions. So you might wonder, then where would the current actually flow in the middle part of the circuit? Now, in those cases, just make an assumption. Let's assume that the current flows under, and let's assume that the amount of current that flows downward would be I1. Using this assumption, calculate I1. If I1 is positive, then your assumption was true. The current would flow downward. If your assumption was wrong, if I1 was less than 0, then it means that the current will flow in the different direction, but the amount of current that's flowing would be the absolute value of I1. So even if your assumption gets wrong, still the only thing you would have to do is change the direction of this current, and the amount of the current that flows would be the same. So it's not a big deal. That was my tip. Now, let's move on to the hardest part of this unit, which is RC, RL, and LC circuits. So let's start off with RC circuit. Now, RC circuit can be divided into two parts. The first part is charging, and the second part is discharging. Now, if we think about charging initially, now, when I explain capacitors, I like to use the idea of portable chargers, because portable chargers are very similar to circuits. Now, consider this C over here, this capacitor over here, is a portable charger. Let's say you plugged in a portable charger to a battery to charge your portable charger, and your portable charger is at 0% right now. What would the current be? Would the current be very high or low? Well, obviously, the current would be really, really high because your portable charger is at 0% and the battery wants to charge your portable charger. So it's going to send a lot of electrons. It's going to send a lot of charges. Thus, I, or the current initially when you're charging, would be the maximum value. Now, how do you find this I? Well, you use V over here and R over here, and you use V equals to IR, or Ohm's law, to find I. Once you find the maximum I, then you can use this formula, I0 times e to the power of negative t over RC, to find the charge in any given time after you start charging. Now, what's interesting is, as I mentioned before, the amount of current that flows in RC circuit is not stable. It changes over time, and how it changes is that it's gonna decrease. Why? Basically because, again, if you think about portable charger, as your portable charger gets more charged, your battery will gonna think, oh, the portable charger is more charged than before, so I'm gonna send less electrons. I'm gonna send less charges to the portable charger. Thus, the speed of the portable charger getting charged will decrease. In other words, the current will decrease. So if you look at this formula, I0 times e to the power of negative t over RC, I0 is the maximum amount of current, or the initial current, because again, the initial current is the maximum current, times e to the power of negative t over c, t over RC, and basically you can see how as t increases, I will decrease. And basically that's the same as what I was just explaining about. And also, of course, you have the time constant tau equals to RC. Now, some people replace this part, RC, with tau to make the formula I0 times e to the power of negative t over tau. But personally, I don't like this because it just makes things more complicated. Now you would have to make this formula, calculate RC, plug that into tau, and calculate I0 times e to the power of negative t over tau. So I personally really don't see the point of using tau in this formula, but there are some questions that literally asks what is the time constant in this circuit. And in those cases, you would have to use this formula tau equals to RC to calculate the time constant. So remember this formula as well. Now, I wrote something here that I didn't mention, that the capacitor would initially work as an ideal wire, which is literally another way to explain the things that I was explaining. Basically, again, if you plug in a portable charger initially at 0%, then the current will going to flow so well, your battery is going to try to charge your portable charger so well that the portable charger will work as an ideal wire, like a connected wire without any elements sticked onto it. However, of course, as the portable charger gets more charged, your battery will think, oh, the portable charger is charged more, I'm going to charge it in a slower rate, and the current will decrease, and the portable charger will not going to work as an ideal wire. It's going to work more like a resistor because it's resisting the amount of current that's flowing toward the capacitor. And of course, if you want to calculate the amount of charge that's charged on your portable charger or on your capacitor, that will be Q equals to Q0. By the way, Q0 is the maximum amount of charge that can be charged on your capacitor. Q0 times I minus e to the power of negative t over RC. And some people might ask, then how do I calculate Q0? Well, that's also not very hard because you know the formula Q equals to C times V. C will be given from your problem most of the times, and V is the voltage difference. Now, voltage difference across your capacitor. Of course, initially, there is no voltage difference because your portable charger is not charged at all. So this is going to be 0, and the amount of charge that's charged on your portable charger would, again, of course, be 0. However, as time goes and as your capacitor is fully charged, now you would be able to calculate Q0, the maximum amount of charge that's charged on your capacitor, because C, again, it's going to be given from your question, and V is going to be same as the V over here. Why? Simply because now that your portable charger is fully charged, the battery is not going to send more electrons, or it's not going to send more currents to charge your portable charger. Thus, I, or the current, will be 0. Now, when I is 0, R over here, the resistor over here, will have no voltage across it. Why? The voltage across resistors are V equals to IR. And if I, or the current, is 0, then V, the voltage across the resistor, is going to be 0. Thus, this resistor is going to be useless. Now, the only elements left in your circuit is going to be your battery and your capacitor. Now, according to the Kirchhoff's rule, if you start from this point and go through this one closed circuit, you will have V plus V and minus the amount of voltage difference across your capacitor. Let's say that's VC equals to 0 because the change in the voltage is going to be 0 when you go through a full closed circuit according to Kirchhoff's law. Now, using this equation, you will be able to see how Vc, or the voltage across your capacitor, is equals to V, or the voltage of your battery. So again, for this V over here, Q0 equals to CV, you can use the voltage of your battery. And for C, again, it's going to be given from your problem. So you can calculate Q0, or the maximum charge that can be charged in your capacitor. Now let's move on to the next part, which is discharging. Well, discharging, everything is literally the same. Now, discharging is, again, you can think about the portable charger analogy. Instead of now charging your portable charger, now you're discharging your portable charger. And when in real life would you discharge your portable charger? Well, that's when you charge something else, for example, for your phone. So when you plug in your charger to your, when you plug in your portable charger to your phone, of course, initially, the current is going to be maximum. Why? Your phone is going to be at 0%, and you have to charge your phone with portable charger, which is fully charged. So portable charger will be like, oh my gosh, we have to charge that phone. We're going to send a lot of currents. We're going to send a lot of charge to the phone. That is why initially, when your phone is at 0% and when your portable charger is at 100%, current will be the maximum. However, one thing different between charging and discharging a capacitor is the amount of charge that's in your capacitor. Well, that's obvious. Again, thinking about portable charger, if you're charging your portable charger, initially, the amount of charge that's in your portable charger is going to be 0%. But if you're discharging your capacitor, or if you're discharging your portable charger, if you're charging your phone using your portable charger would initially have 100% battery or full charge. Thus, the maximum amount of charge, or Q0. So that's the only difference. That's why if you look at the charge formula, when you're charging your when you're charging your capacitor, the formula for Q is Q equals to Q0, or Q maximum, times 1 minus e to the power of negative t over time constant. But if you look at the formula for Q when you're discharging your capacitor, you can see how it's Q equals to Q maximum times not 1 minus, but e to the power of negative t over time constant. Why? Because initially your charge would be maximum, not 0, when you're discharging your capacitor. So that's what's interesting. And of course, if you fully discharge, then again, your capacitor is going to work like a disconnected wire. Why? Again, think about portable charger. If you fully discharge your portable charger, if you fully move the battery from your portable charger to your phone, your portable charger is going to be useless. It's not going to induce any more currents. It's not going to send more charge or current to your phone. Thus, it's going to work like a disconnected wire. Now, I hope that made sense. And now I'm going to move to RL circuit, but my Zoom meeting time is going to end in a minute. So I'm going to first cut this recording and start another recording soon. So you can see that in the second video. In the second video, I'm going to explain about RL circuit and LC circuit. So see you in the second video. Bye.